Today, we finished global rigidity last time in terms of the generic characterization in 2D. So now I want to do something slightly different. So I want to basically start thinking about things a little bit different to generic bar joint structures. But to start with, I'm going to go through what's kind of a fundamental idea in rigidity, the idea of coning. So we did very briefly describe this at some point, but I want to go into the details. So given a graph, we can construct the cone of the graph. So if G is a graph, then G to the superscript C is going to be the cone. And it's simply the graph obtained from G by adding exactly one new vertex, but joining it to all existing vertices. So it has degree exactly the largest it possibly could. It's adjacent to everything. And so what we're going to show to start the lecture is that a graph G is rigid in D dimensions if and only if the cone is rigid one dimension up. So adding a vertex adjacent to everything transfers rigidity from one dimension to the next. Okay, so I guess the sort of easiest thing you could think of, well, does it even transfer the counting condition? So for example, if I take a graph that's minimally rigid on the line, it must be a tree. If I take the cone of a tree, do I get one of these 2-3 tight graphs that we had in the two-dimensional characterization of rigidity? If you just play with the combinatorics of the counting condition, it's not too hard an exercise to show that a graph is D-sparse if and only if its cone is D+1 sparse. And in particular, it's D-tight if and only if the cone is D-tight. So the combinatorics works, but obviously we know the combinatorics is not sufficient for rigidity in dimension at least 3. So proving the rigidity goes when D is greater than or equal to 3 is more complicated. Okay, so coning was introduced to rigidity in a paper about one-story buildings, I think, by Whiteley in the 80s. And so what he showed is exactly what I was just saying. So the theorem of Whiteley is that the graph is rigid in D dimensions if and only if the cone graph is rigid in Rd+1. And in fact, what Whiteley proved is a bit stronger than what I've written here. So what I've written here is the generic statement. So there is a generically rigid realization of G in Rd if and only if there is a generically rigid realization of the cone in Rd+1. What we'll see in the proof, which is what Whiteley did, is we will take a particular framework and show that we can transfer it from one dimension to the other, and the exact infinitesimal motions of one transfer exactly to infinitesimal motions of the other, and the start and finish ones are particular realizations. So it's saying from this particular realization I get another particular realization, and all the properties transfer. It's not saying as long as you're generic, these things nicely happen. So it's a bit stronger, as you'll see. The proof that I'm going to do, and we'll go into a bit more of why it's true after that, but the proof I'm going to do is really a first-year linear algebra exercise. If you see what to do, I'm going to take the rigidity matrix and do a sequence of row and column operations on it. This is going to mean it's going to be a bit horrendous on the small screen to be able to see these matrices as we go, but it might be that you just want to note down the row operations and column operations as I go and check them for yourself later, or it might be that you want to pause me and get me to wait while you check that I haven't made any mistakes. And there is a high chance I've made a silly mistake as I've gone along, but believe me that the row operations do work out if you haven't made a mistake. So to make it a bit simpler for myself, I'm just going to take D equals 2. So I've only got X's and Y's and Z's from R2 to R3. So as I say, we're going to start with the framework in D+1 space, so in R3, with the cone framework and the rigidity matrix of that. And we're going to do a sequence of operations. And then at the end, we're going to do a little projection to move down to the right size for a two-dimensional rigidity matrix and show that given any framework G, the cone of G, P, we can construct a different realization P bar, which is now in R2 rather than R3, but that this one has exactly the same infinitesimal motion properties. All of the linear algebra properties are the same. The dimensions of the kernel and co-kernel, they all transfer nicely. So dependencies and independence, rigidity, it all nicely transfers. Okay, so let V be the new vertex in GC, the cone, and let's pick two other vertices in V. So they're just arbitrary vertices in the graph. And so I is going to be xi, yi, zi, j is going to be xj, yj, zj. And the special cone vertex, I'm actually going to put at the origin. So put it 0, 0, 0. So I hope you believe me that, okay, the rigidity matrix, there may be many, many more vertices, many more edges, so many more columns and rows. But if I just show you the effect on a typical edge between typical vertices I and j, and between those given vertices and the cone vertex, and so I look in the triples for columns for I, j, and v, and you see what the row and column operations I do here, you'll be able to see how you would adapt it to change every single row and column in the bigger matrix. So obviously this is just one subpart, but I think you'll see how to adapt it as we go. Okay. So, and notice, well, I said P V is 0, 0, 0, but in this first one I've actually put it in, even though it's not really there now because it's at zeros. It'll disappear in a moment. So what's our first observation is that if we remove the column triple for this cone vertex V, then what we've done is said that every infinitesimal, by remove I mean just consider the smaller matrix without it, then what we've done is insist that every infinitesimal motion at V is 0. So that vertex P of V at 0, 0, 0 is unmoved by every single infinitesimal motion. So what we're doing is pinning the location of that vertex infinitesimally. So we're saying that this PV can't move, but everything else moves as normal. So we've got rid of the three columns for V because we pinned that vertex. And here where we had P of I minus P of V, the P of V is 0, 0, 0, so it disappeared from seeing it, and here it was P of J minus P of V, and the 0, 0, 0 disappeared. But otherwise, from up there, which you now can't see, to here, nothing's happened. So it was really pinning these three columns in the infinitesimal motion, and hence we can just discard them. Okay, and so now we start. As I say, I'll give some intuition for why where this comes from after the proof, but now we're just going to start I guess, horrendous sequence of row and column operations. So luckily you can see them both. So the changes, the first change is that I take, so R sub ij means the row for ij, etc. So hopefully that's relatively clear. So I take the row for ij, I subtract the row for iv, so the xi minus xi cancels. And then I also take the negative of the row for ij. So xi and xi cancel, I get minus xj, and then the negative gives me xj. And similarly, the yi's cancel, and the negative gives me yj. The zi's cancel, the negative gives me zj. And I'm also doing rij minus rjv. So obviously over here, I had no effect with the first one. Here I have no effect with the second one, but over here, the xj's cancel and the negative, then the yj's cancel and the negative, the zj's cancel and the negative. So from here to here, again, it's just elementary linear algebra. And then we're just going to continue for a little bit with this kind of sequence. So the next one is we take the row for the edge from I to V and divide it by 1 over Zi. So this becomes this. Obviously zeros weren't changed, and the row for JV divided by 1 over Zj, so this becomes this. Okay, so that's, unless I made a mistake, hopefully still straightforward.
Tony?
Yes.
Why are the Zi's and the Zj's non-zero?
Oh, that's a good point, yeah. So I didn't say any geometric hypothesis at all, but so I am assuming that I want to say that's all I'm assuming. So what we're going to get to is points on the sphere, what we're really going to be thinking of in a bit. And so what exactly you're pointing out is the points on the equator of the sphere are a bit weird, and they turn out to be like points at infinity. But this is a bit of a story I'm not going into. So I am just assuming the zi's are non-zero, and that's really I'm talking about finite points.
Got it. Okay.
So yeah, sorry, I am definitely assuming that all the zi's are non-zero. I think that's all I'm assuming, but we might see in a moment. Okay, so we're up to this matrix. Now we're going to replace Rij by this sum of all these things. And I'm just going to say, check that one for yourself, but you can see that these two rows didn't change. And we've just replaced xj by minus xj plus zj times this thing plus zi times this thing. And this is what you get. This just looks horrible, but it's just what you have to do along the way according to the sequence. Okay, so, and then there's another sequence of operations. So now I want to multiply this kind of weird looking row by 1 over zi zj and multiply, oh, that should be an RIV, I guess, and an RJV. So multiply those by 1 over zi and this one by 1 over zj. So we're doing these 3 different scalings of our various things. For example, our xi over zi has become xi over zi squared. Our 1 has become 1 over zi, and similarly the 1 has become 1 over zj, and then you get these weird things. Now we start doing columns rather than rows. So now I'm going to multiply each column under the vertex I. So this column, and this column. Multiply them all by zi. So this one's going to cancel, this one's going to cancel, the square is going to cancel the square, and this is going to cancel. And so that gives us down to what you see here. And also columns under j, so that's these 3 by zj. So the zj, and the squares are going to cancel there. And we end up with this thing. And now it's in a nice convenient form, because so now we have,
can I interrupt again?
Yeah.
I'm sorry. I thought we just divided by zi, and now we've multiplied by zi.
Yes.
Like, how come we didn't just come back to the matrix that we started with?
The first one was rows, and the second one was columns.
I see. Okay. Yes. Okay. Sure.
So yeah, for some of the entries, we were just being silly by turning 1 into, so here I think we just turned 1 into 1 over zi back into 1 and didn't do it. But in some of the others, the change from row to column operations did have a, so this entry did genuinely change from what it was before we did the scalings. So yeah, I mean, I really want a few boards so I can just jump back and forth a bit easier. But all we're doing, what I'm really trying to convince you is there exists some sequence of row and column operations that transfers the rigidity matrix into a nice form that I want. Okay, so now if we notice this entry, then in the column it's the only non-zero. So if I do a sort of projection down to a smaller matrix by ruling out all of this, I know that 1 will have affected the rank by 1, but it's had no other effect. So I can just go to a smaller matrix, and I can do the same here because this column has 1 non-zero and it's a 1 here, and I can get rid of that. So I get rid of the z coordinates of vertex I and vertex j by doing this and getting rid of the rows from an arbitrary point pi to the cone vertex, an arbitrary point pj to the cone vertex. So the z coordinates of vertex I and j have gone, and the edges from those vertices to the cone have gone. But I know exactly that as I move between them, I would just changing the rank by these 2. Okay, so after you've got rid of the blue and the reds there, you get to this matrix. So now I only have the edge between I and j, the edges to the cone have gone, and I only have the x coordinates and the y coordinates of the two vertices. But this is exactly the rigidity matrix for my smaller framework in the smaller dimension, where with this p bar that I mentioned, which now I can define for you, that p bar of I is equal to xi over zi, yi over zi. So in effect, what I've really done is I've took arbitrary points in 3D and I've divided them by their z coordinate, as long as it was non-zero, to put them on the plane where z equals 1. And then I've forgotten about the z coordinates and think about them as just living inside that plane, i.e. as if they're a two-dimensional object. And since all of these operations preserved the rank, or at least when the rank did change, we knew exactly how it changed. Here we can say that this last one is rigid if and only if the first one is rigid. And so we proved the result. Okay. Yes, so I give a reference to a much more recent paper than the one for the theorem by Yasser F. Tekhari and a group of us from a couple of years ago, where what was not covered in here was exactly Will's point, that we had to assume that these points were finite points in the projective sense. And so if you have points on the, I like to think of it on the sphere, if you have points on the equator of the sphere, then you need to work a bit harder, and the transfer is a bit different. And so that's what this paper was about. But I think it expresses the transformation I've just said, with no matrices, just as maps, rotations, inversions, and kind of things, just to show nicely how you can move between one dimension and the other using the sphere and things. So this is a nice reference, I think, to get some more intuition. But what I want to do is, first, I'll talk about spherical frameworks so I can show a bit more of the picture to give a bit more understanding for what we just did. But I also want to take this opportunity that we used, this cone vertex was pinned, and I want to talk about pinned frameworks more generally as well, where maybe there's more than one vertex that's pinned, or maybe the restriction on a vertex is not just this is completely pinned and all the rest are completely free, but maybe this one's restricted in its motion in some way as well. Okay, so what we just did was we had this cone vertex at the origin and said that was completely pinned. So, and every other vertex was adjacent to it. So for the vertex I adjacent to V, there was some length for the edge, say R. We can think of R as the radius of a sphere whose center is this pinned point V. And then J had some other length, R dash. And so J was forced to stay radius R dash from the center V of this sphere. So if you like, what we were thinking about was frameworks where the vertices were constrained to lie on some family of concentric spheres that had all had the same center, and it was the origin where PV lived. But what we were actually doing in the raw operations in some sense was we were sliding vertices along. So we were taking a vertex from xi, yi, zi. So let's suppose that zi was some, I don't know, is equal to 10, some big positive number, and we were dividing. And so we were bringing it in from wherever it was to the plane that is distance 1, where r equals 1, away from here. So now it lay on, well, now I'm saying xi over zi, yi over zi, zi over zi, to bring it to the right distance away. And so we can do this to all of our vertices and keep moving them all along these rays until they're all the same distance. So they're all distance 1 from the origin. And then it would actually be one sphere rather than concentric spheres. And so as I showed in the proof, what we were really doing is we were doing this vertex by vertex. So you could have families of concentric spheres, as many as you want, but one by one, we can just slide our vertices to all lie some specified distance, we might as well say 1, from the center of the cone. Okay, so what that means is we can continue these row and column operations until framework lives on the unit D sphere. And so we can think about rigidity on the D sphere using this matrix that we have. Okay, so again, I want to just think about the two-dimensional case. So use S2 to denote the sphere, this unit radius sphere centered at the origin in free space. So it really is just the solutions to this simple quadratic equation. So what we had in the cone case, we had this rigidity matrix. So we deleted whatever the cone vertex was, say it was V, we deleted the columns for that, and we'd set P of V equals 0, 0, 0. So this PVI was really PVI minus 0, 0, 0, and so was this PVJ. It was PVJ minus 0, 0, 0. And so this was the schematic of the rigidity matrix we were just working with. But I want to reinterpret this in a different way now. And so what I want to interpret it as is just thinking of this is the same. Nothing's changing here. This is just the constraints between edges. But I want to think of this as being the constraint that the vertex VI, the framework point P of VI, moves on the sphere rather than being free to move off into 3D. So I don't want to think of these as edges anymore, edges from VI to the fixed cone. I want to think of them as vertex constraints on the vertex VI, and that this constraint forces that vertex to live on the sphere. So instead of having, let's move over here. So instead of having a graph with lots of edges like this, and then the edges around the outside, I want to think about a graph that's just like this. And so there are no edges to the middle, but I want to constrain it to the sphere by having conditions on the vertices instead. So I'm going to reinterpret these rows instead of as edge rows to the cone as vertex constraints. So in particular, what I want the constraint to be is that this vertex should move infinitesimally in the tangent plane to the sphere at this point. And so what I want is for the infinitesimal motion to be in this tangent plane. So I want the infinitesimal motion to be orthogonal to a normal vector to the tangent plane. And so that condition says my normal vector, given this, a normal vector would be something like this. But because rows of the rigidity matrix we can scale, I can just forget the twos and I just get the x, y, z for a point x, y, z on the sphere. So it really is just whatever the point is goes there as well. It happens to be this nice coincidence in the case of the sphere that the normal vector to PVI you can just think of as PVI itself. And so nothing much changes. It's just apart from the interpretation of what these rows and entries mean at the bottom half of the rigidity matrix. Okay, so using this, we can see the following theorem, so that the framework on the sphere is rigid if and only if the cone framework is rigid in free space, but we know that from the theorem before is rigid if and only if this framework in R2 is rigid. So we have rigidity on the sphere is equivalent to rigidity in two-dimensional space. So on S2 is equivalent to R2 for rigidity. And in fact, this actually all extends. So SD and RD are equivalent. A graph is rigid in one if and only if it's rigid on the other. So again, I've said here, this P bar is from sliding every vertex to the plane Z equals 1 and discarding Z coordinates. And the P on S2 and the PC are exactly what sort of thing I had here. So this would be P, and then PC is exactly the same. I know I haven't drawn them very well because I've drawn different graphs, but or maybe I've just drawn it badly. That this vertex and this vertex are the same in PC and P. The difference is only that PC adds the cone vertex. Okay. Oops. Okay, so and then just to draw it in a little schematic picture, this is what we were really doing in the matrix manipulations we had earlier. So we were taking a point that lay some distance from the origin, say it happened to lie inside, and we were just able to move it along its cone ray through the unique line in free space through the center of the sphere and the point on the sphere. We can move it to the plane, and so you have some other point, you can move it along here, and then basically Will's comment was what happens if you have a point on the equator, z coordinate is 0, and then this line takes you off to infinity, and you need to be a bit more careful and include points at infinity, which can be done, but it's just not what I want to get into. Okay.
Yeah, Tony. So
yes.
I guess if we had such a situation with the points on the equator, we could just rotate slightly, perturb the sphere, just rotate the sphere, and then that wouldn't happen any longer. So that makes.
So this is true, and we do this in the paper with the many authors, F. Tekhari et al. That I mentioned, but it's not quite something that's going to be useful for rigidity without a bit more work. So if there's exactly 2 points on the equator, then that's fine, because any 2 points on the sphere, there's a great circle through, so it's just like any other great circle. But if you have, say, 3 points on the equator, then a sort of flat triangle or a flat something else, some bigger shape, is not generic situation. So if you take at least 3 points on the equator, you can rotate, I agree, and you make that all those points will now have non-zero z coordinates. So if they're on the upper hemisphere, we can just do this, and if they're on the lower hemisphere, you can do let's say it's on the lower hemisphere here, you could do an inversion to put it here and then do the same process again. And that's all fine, but because they were on the same great circle in the equator, when you rotate, they're on the same great circle. Now it's something like this. So they'll be collinear in the realization in the plane. And so, for example, if it was a triangle, it would become a collinear triangle, and you get a dependence when you would have had an independence if they weren't collinear on the sphere. So that paper goes into the combinatorics of how to characterize rigidity in the plane where you don't have generic, but you have some collinear bits as well. And so you're exactly right that you can just rotate, but it creates a bit of a more complicated story to deal with it fully.
Can I make one other comment? Because maybe you're going to say this, but if you're not, then I'm wondering why, whether it makes any sense. We're looking at infinitesimal motions on the sphere now, and I want to think about that as a vector field, I guess, on the sphere, because it's not so obvious that it's defined everywhere on the sphere. It's only defined maybe at the points on our framework, as I'm mulling this aloud. But what I really wanted to get to, of course, is it's somehow leveraging the Harry Ball theorem, or the situations where we would force our vector field to have a fixed point, and then somehow use that to deduce something about rigidity. That maybe is too much to hope for, given that you only have a vector field defined at the points of the framework. Yeah,
I think so. Yeah. To be honest, I never thought of this, but as you say, we only have these tangent planes at the points that are relevant. Of course, you can have the tangent planes everywhere, but only the ones at the points will give us the nice tangent vectors for the vector field. So I don't think I have a sensible.
Maybe it's not a sensible question, really. Comment anyway. Okay.
I mean, if anyone else has a remark on that, then feel free.
Sort of question. Should we think about infinitesimal motions as motions on the tangent plane at a point, or motions in the tangential direction at a point on the sphere?
So I think I missed part of the comment. Do you mind repeating, Jack?
So when we're thinking of an infinitesimal motion for a point on the surface of the sphere, should we just think of that as in the direction of, or in the direction of some vector in the tangent plane at that point? Or,
yes.
yeah.
So I have some point on the sphere, then any infinitesimal motion of it should keep it within the tangent plane. So really what you think of is you have the usual infinitesimal motion condition for your edges. So you have the dot product, or let's say u's of the infinitesimal motion should be 0, but you also have the condition that the infinitesimal motion I for the vertex vi should be orthogonal to the normal to the surface at vi. So we have a normal to the surface, say, sticking vertically, almost vertically out from here, and we want our motion to be orthogonal to it to stay within the tangent plane. Did that answer your question?
Yes, thank you.
Great. Okay, so actually that question's really well timed, because it brings me on exactly to what I want to talk about just briefly, is that there's not necessarily all that anything hugely special about the sphere. So we could replace the sphere with a different surface, and then if we go back, so what will happen, we'll have a rigidity matrix like this one, but we would replace these entries, which were the normal vectors to the sphere at the point, with different normal vectors depending on what surface we picked. And the effect of that is that these ones that we had here were exactly the ones that made the rank of the rigidity matrix exactly what we wanted. So for example, if we're taking the 2 sphere, then it would give us a 3-dimensional space of infinitesimal, trivial infinitesimal motions, the 3 rotations, that matches up with the plane, which has 2 translations of 1 rotation. If I pick a different surface, then these entries will be different, and that will affect the size of the kernel and the maximum possible rank of the rigidity matrix, and hence you get into new combinatorial questions. So I just want to briefly mention one example. So a sort of natural surface you might consider is the sort of infinite circular cylinder. So you just take, for example, the polynomial x squared plus y squared equals 1, and so you have an infinite translation in the z direction, and then you have a radius 1 cylinder around it. And so here your normal vectors will really be of the form xi, yi, 0. So the 0 instead of zi will affect the possible ranks and prevent some of the possible vectors being in the kernel of the rigidity matrix. In fact, it allows a translation, so it allows one the sphere doesn't, but it rules out 2 of the rotations that the sphere does have. And so you have a different rank, and hence you have a different combinatorial challenge. And so just to be very brief, the sort of rigidity matroid in that context, where you have your points live on the cylinder and you have edges are just still Euclidean straight line distances, you can think of it as a matroid contraction of the row matroid of this matrix, because we care about just a set of edges rather than a set of edges plus vertices. And what we want to know is that a subset of the edge set is independent if the entire rows for all of those edges f plus the vertices incident to f give you a linear independent set in the rigidity matrix. So this is, if you want to Google it, this is a sort of matroid contraction kind of operation, but you can look at the independence of the same big matrix with the different normal vectors, but ask whether the set of edges is independent, which is really what we were doing for the sphere, but there we were able to translate the problem between the 2 settings. Here we have to argue from scratch, and so I'll just mention briefly the characterization on the cylinder, which is really the characterization in the plane with one small change to the combinatorics. So instead of having 2v minus 3 edges, we have 2v minus 2. And instead of having at most 2x minus 2 in any subset, induced by any subset, we have 2x minus 2 rather than 2x minus 3. So this is coming exactly from the fact that the cylinder only allows 2 isometries. It only allows a translation and a rotation around the axis. So, I mean, the proof is a fair bit more complicated than what I've said, but it's basically studying this class of graphs rather than the class of graphs we had in the Leman theorem. And there is one more complication that I didn't really say on the sphere, but maybe I should have, and I'll say here, is that the word generic now has to mean something different. And this was true on the sphere too, because generic in this course has meant algebraically independent coordinates of the vertices. But if you live on the sphere or the cylinder or some surface defined by a polynomial, then the fact you satisfy the polynomial that defines the surface says you can't be algebraically independent. So the generic in the context of the sphere is sort of a nearly generic, or in the cylinder again is a nearly generic, where you must satisfy here the polynomial equation for the cylinder. So any PV xi, yi, zi, even just the one vertex, it can't have all three of these being algebraically independent because the x depends on the y. So you have generic modulo the polynomial that defines the surface. But this is I guess a bit of a side issue because I don't want to go into the proof of this. I just will briefly mention that other surfaces have also been studied, but I won't go into that. I will mention a little bit about global rigidity next, though. Okay, so let's go back to coning. So we were able to show, we were given any framework in our d+1 with a cone vertex, as long as the z coordinates were non-zero, we were able to do this sequence of row and column operations and then projecting down to RD and look at the graph without the cone vertex and have rigidity transferred from one situation to the other. Exactly, it's completely geometrically transferred. So now I want to think about the same question for global rigidity. And so this was studied by Bob Connolly and Walter Whiteley in 2010, except, and I direct you to their paper for examples, but it's not true geometrically to the same extent as it was for rigidity. But what is true is the generic situation. So if we talk about graphs, so a graph is globally rigid, generically globally rigid in RD, if and only if its cone is generically globally rigid in RD+1. So we can do that transfer. Their proof is to use the equivalence of generic global rigidity with the existence of a maximal rank equilibrium stress. And so they show that equilibrium stress rank can be transferred. And again, I don't want to go into the details. I just want to flag up the theorem. I will say that from the rigidity result, because dependencies were also transferred, it was linear algebra, it was transferring the co-kernel and the kernel and everything. We already really know that redundant rigidity transfers. And it's also easy to see that if a graph is deconnected, then adding a vertex adjacent to everything increases the connectivity. So the Hendrickson natural necessary conditions for global rigidity transfer sort of trivially from what we already saw earlier in the lecture. So the difficulty in this theorem is that redundant rigidity and deconnectivity are not sufficient for global rigidity. So somehow they had to work harder and used equilibrium stresses to show this nice result. Okay, so I mentioned this nice result now because it means we can give the analogous statement for global rigidity that we gave for the sphere a few minutes ago. And that's, again, that they noted this, that a graph is generically globally rigid on the sphere if and only if it's generically globally rigid in the plane, and hence if and only if by the theorem from last time, the graph is free connected and redundantly rigid. And the redundant rigidity on the sphere and in the plane is the same, so I could have written R2 here if I'd wanted. But generic global rigidity on the sphere is completely characterized by this paper about coning. Okay, so I want to move on to something a little bit different. So if anyone had questions, this would probably be a convenient time.
Is there much that's known about projecting onto like less, I don't know, other surfaces other than spheres and cylinders, or is there some like general theory about projecting onto surfaces, or not really? Or is it already hard enough with spheres and cylinders?
So in terms of rigidity, maybe I glossed over this, but it has true that other surfaces have been studied. So I could say a little bit about that.
Sorry,
so,
yeah, you did mention that. I forgot.
So we have this sort of count where really this is the dimension. And if I move from the plane to a two-dimensional nice object like a surface, then the two will stay the same. But this 3 really came from the fact the plane has 2 translations and 1 rotation. And so as I said, for the cylinder, it changed to a 2v minus 2. The options available for a nice surface in R3 are changing to 2v minus 2, 1, or 2v minus 0. And so that there are papers that discuss and characterize infinitesimal rigidity in, I said, this context, in this context too, and in this context, or at least with a caveat or two. For global rigidity, I mean, maybe I should say that an example of a 2v minus 1 surface would be a torus or a cone. And for 2v minus 0, you could have like an ellipsoid, so a sphere where all 3 of the radii are different lengths. And for global rigidity, we said here it's true for the sphere. We get a nice characterization like this. For the cylinder, there's I did this with Bill Jackson. Maybe it's a few years ago now, 2018 or 19. We characterized generic global rigidity on the cylinder, but actually it was very hard, and it was quite a bit harder than this one. And if you want to move from the cylinder to a different surface, so a surface in sort of this class or a surface in this class, then I think that there's quite a lot more work to do. I have a recent PhD student who started with me who is looking at this kind of problem at the moment.
Thank you.
Okay, so let me say a little bit about pinning more generally. So I mentioned you can pin more than one vertex, which we haven't had yet. And I mentioned you can, instead of pinning an entire vertex, you could think about, say we live in 2-dimensional space and you have this vertex, instead of saying it's locked into position, you could say, well, maybe it moves on this fixed line and moves in a 1-dimensional way instead. And so this is really the subject that we call linearly constrained frameworks. So let's just see what I said here. So the cone vertex was pinned, and you can imagine in applications, if you're an engineer perhaps, then maybe you do want to have certain parts of your mechanism grounded, say. So you do want to have pinned or restricted to a track or something like this for some parts. So this is what I'm going to do. So I'm going to consider, for, well, however much time we have left in this lecture, frameworks in RD with additional constraints that require some vertices to move in given affine subspaces. So I'm going to say, oh, this vertex happens to be forced to lie within this given plane, or this vertex is forced to move on this line, and this kind of thing. The way I'm going to do this is by working with looped graphs instead of simple graphs. So we're going to have our usual vertex and edge sets in the graph. We're also going to have a set L of loops. And I know loops could just be a type of edge, but I specifically want to separate out non-loop edges from the loop edges. But as usual, we're going to have no multiple edges. And so now we're going to define our frameworks via 2 maps rather than 1. So we're going to have a map that assigns positions to the vertices and a map that assigns normal vectors to the loops. So if there's a loop at a vertex, the map gives you a normal vector to some line, and the vertex is forced to lie on that line by this map Q. I mean RD, so instead of line, I should have said hyperplane. And so now we have a triple from our looped graph, G equals VEL, and our realizations P and Q. So the triple GPQ is one of these linearly constrained frameworks. Okay, so here's an example. So here's a graph with 2 loops at the vertex U, 1 loop at V, and no loops at the third vertex, which I haven't given a name, W, say. So W is free to move anywhere it likes in R2. V has one loop, so it's constrained to move on some fixed line. U has two loops, and I'm always going to assume the loops are at least linearly independent, so that we never give the same constraint twice. So if there's two loops, and we live in 2 dimensions, two loops at a single vertex, there'll be two lines through the same point that intersect only at that point, and hence this vertex U is pinned on the intersection of these two lines. So in my linearly constrained framework, this vertex U is fixed. The triangle could only then rotate centered at U, but if it rotates, then V would come off. It would go back on at some point, but it would come off. So at least infinitesimally, there is rigidity is present because V would have to move off the line that it's constrained to in this framework. So this is an example of a rigid linearly constrained framework in 2 dimensions. It's not globally rigid because I could keep going and put V back on this same distance, but still on this line over here somewhere, I guess. Or I could just take a reflection through this whole part and move W over to here somewhere as well. So this is it's got a lot of color on now, but this is a graph which is rigid, but not globally rigid, as a linearly constrained thing. I haven't formally defined either of those, but by rigid, I mean infinitesimally rigid, and I mean the only infinitesimal motion is the zero motion. And I think there is a question in the chat, I just have to find it. What if 2 or more non-adjacent points are constrained to the same line? So this is not going to happen in what I'm thinking of. So my linear constraints are at the vertices. So it's true that this linear constraint and this one could give you the same line, and they would be, say, parallel if the points were distinct, or they'd be on top of each other if there was some geometric coincidence. But what I'm going to say in a moment is that I'm interested in the case where the Q is generic. So each loop has to be algebraically independent of the other loops. So and the points are also algebraically independent. So it's never going to be the case that 2 vertices will be constrained to the same line, because it will always be, it would break the genericness.
Tony, could you say again what Q is? It's a map from these loops, but I don't understand what it's telling you. It's supposed to tell you that you're on this line, right? But
yes, so Q assigns a normal vector to some hyperplane. So it's saying, well, here it's at so the Q really does depend on V, but L tells you that because a loop in L is instead of some vertex of V.
Mm-hmm.
So it tells you a normal vector at this point. So really it just gives you some vector, say in free space, if we're in D equals 3, it gives us some vector through the point where the loop vertex lived on, which then you can think of as a normal vector to some plane, and the vertex is now constrained to only move infinitesimally in this plane. The same way we had normal vectors to a tangent plane for a surface.
Yeah, okay.
The Q is given the normal vector, and then there is some plane that now is not associated to any surface, but it still exists, and we still force it to move within it.
I see. Yeah, okay, thanks.
Thanks. Okay, so I actually, again, the question is very well timed, because by doing this, we can think of linearly constrained frameworks as frameworks on surfaces. It's just that we didn't know in advance what the surface was, so we have to now fit some surface to this, so that this plane that the vertex is constrained to is the tangent plane to some surface at this point. And we can do that one by one. If every vertex had one linear constraint, every vertex, say when we're in 3-dimensional space, every vertex has one linear constraint. So every vertex has some plane it's constrained to. If we think of all those planes as a tangent plane for some surface, maybe it's some weirdly complicated or crazy looking surface, but we can think of it that way. And so in particular, if you allow your Q to be very non-generic, then you can think of the sphere case as a special case. So there, each vertex has the one linear constraint. They're just all nicely related and give you the nice smooth surface, whereas in general, you might get something much wilder. So, and as I said in the answer to Alex's question in the chat, we're really going to consider this map to be generic, and then because that allows us to give a combinatorial result. Because if we don't assume the map is generic, then we include frameworks on surfaces, like we were talking before about the sphere and the cylinder, as special cases, but the combinatorics is different as the surfaces change, as I tried to indicate. So you really wouldn't have much chance without knowing something about the nature of the normal vectors in the map Q. Okay, so let's assume that the map is generic. And now we can state an analog of the Pollaczek-Geringer-Leman theorem. So this is obtained by Ileana Stranu and Louis Ferran in 2010. They called them slider frameworks, but I like this linearly constrained name instead. So a generic linearly constrained framework. So I have my looped simple graph and I have the two maps P and Q in R2. This is minimally rigid if and only if the number of edges plus the number of loops is twice the number of vertices. And we have two subgraph inequalities. So for every possible subgraph, it must be true that the number of edges plus the number of loops is at most twice the number of vertices. But also, if you have no loops, you can't violate the Leman condition itself. So if you have no loops at all in a subgraph, then you must have the number of edges being at most twice the number of vertices minus 3. As long as you have at least two vertices. The point of this second condition is that if we didn't have it and we just had these two conditions, then we would be allowed to do something like take K4 and add two loops. And this is clearly not going to be okay because it violates the two-dimensional condition. So it has the right number of edges, but one of the edges will be dependent in the K4 because it's already dependent as a plane framework with no loops, and so adding the extra rows for the loop constraints or vertex constraints can't get rid of that row dependency, and so we're going to end up under the full rank. And so we have to have something like this as well as the standard inequality in the form that we have here. I was going to go into the proof, but I'm already coming to the end, so I think I will delay the proof until Monday, especially since the drilling above my head is getting irritating. So I think I'm going to stop and ask for questions at this point. Otherwise, we will continue on Monday. So over to you guys.
Hello, Tony. Can I have a question?
Yeah. Hi, Faith.
Yeah. So I was thinking. So if we have a framework in D dimension with D+1 vertices. So, and then you do the coning. So you connect every point except 1 point. So one edge is missing. Then this means there should always exist the equivalent framework in RD+1, right?
Sorry, you'd have some framework on D+1 vertices in D-dimensional space?
Yeah, and they add a new vertices. So so you connect every vertices except one. So it's the coning with one edge missing.
Okay. So instead of coning to RD+1 by adding a vertex adjacent to everything, it deliberately misses 1 point but hits everything else.
Yeah.
Okay.
Yeah. Then this framework should have some equivalent framework in RD+1. Right? So this is my question: is there this should always have a equivalent framework in one dimension or higher?
So if this one was rigid, then this one, so G-co minus this edge E, will I mean, okay, so if this is minimally rigid, then this one is flexible in RD+1. So that the coning theorem said that the minimal rigidity of G would transfer to the minimal rigidity of the cone. And so now you've took E out, it'll be flexible, but I'm not quite sure what you're asking.
I'm asking if this for this GC minus E, there is a equivalent framework in D+1 dimensions.
What do you mean by equivalent framework?
It means every edge is the same. So you can change the length of the missing edge E. So by changing the length of the E, you can actually get a framework in a higher dimension. So from RD to RD+1.
So the theorem said, given a framework in RD, we can get one in RD+1 that's rigid. But since you're taking one edge away, I'll be able to have an entire family of frameworks in RD+1 with all the same edge lengths except for E. So this distance for E will keep changing, and there'll be a one-dimensional smooth manifold of equivalent frameworks for GC minus E. But then it takes a proof, but then there will be a finite number of points where the length of E comes back again, and you'll be able to find other equivalent frameworks for GC.
Yeah, this is my question. So this G doesn't have to be rigid, right? To have this one-dimensional smooth manifold, so you can always lift it to one dimension higher. If the conium is one edge missing in the conium, right?
But so I think I'm missing part of what you're asking, because you can always take so let's say I have some graph. I can always take it and say I'm thinking about it in the plane, regardless of whether it's rigid or not. I can always just lift it up a dimension by putting zeros in there, and then ask, are there less trivial examples of equivalent frameworks in the higher dimension? And typically you can at least translate and rotate and get more trivial examples that are also equivalent. And then whether it's non-trivial or not examples will depend on the structure of the graph a bit. But I'm not sure it's really related to the coning operation. So maybe I misunderstand what you're asking, Faye.
Yes. So I want to ask is if you do the conium, then somehow you could stack in that dimension, right? For some particular edges, so you could stack in deep dimension. But you have one edge missing, then you can always lift it to one dimension higher.
But so that regardless, if you just take some framework in RD, then whatever, absolutely any graph you like and any realization P, as long as the final coordinates are non-zero, you can always take the cone graph and lift it up to some other realization in RD+1. And so in particular, what the realization looks like is you keep everything in G flat, and think of it now instead as a copy of RD inside RD+1, and add your new vertex adjacent to everything. And so you can just always do this, and then all the lengths in here are obviously the same as the previous one. So I'm not quite clear what property it is you're worrying about when you go up a dimension.
If some the length of edges are fixed, right? So if the length of the edges are fixed when you're adding the new vertices, then you could stack in that D dimension. So add one vertex, and the edges the length of the edges are fixed. And then you're adding deep. You add, like, for example, D. You connect to D points in RD, and then the D edges are fixed for some particular number. Then you could stack there, right? Your framework was stuck in RD plus RD. So yeah.
So by stuck in RD, I guess you're thinking about something like universal rigidity, where you might, for example, have a graph like this, and you realize it in R1, and because you had one really long edge, which was really the sum of the 4 short ones, then this is locked into R1, even if you think about it as a graph think about this graph G as living in RD for any D. You can never do anything other than have it live within a one-dimensional subspace of RD. But the coning operation I'm talking about is very different to that, because whatever graph we have, whether it was locked into R1 or it wasn't, I can still add a new vertex and join it everywhere. And the locked into R1 property was very dependent on the geometry of the realization, that it was like that rather than being like a zigzaggy one, which would be easily able to open up into R2. And so when I add the cone vertex, these guys will all be allowed to move to a more generic situation, like in the theorem statement, and hence you'll lose the fixed into the lower dimension. So I'm sorry, I'm still not quite following exactly what the question is, I don't think.
Yeah, so I draw on the screen.
Yeah.
So this is.
Let me give you some space.
Yeah, so this is so I have 3 points. All right, so if I add a new point like this, so 3 edges. So this is actually this was stuck in R2, right?
What do you mean by stuck in R2? Because we could have this is.
So stuck in because my edge the lengths are fixed. And now I remove one edge. So this will be this can be lifted to R3. So my question is this true for any dimension higher, for any dimension instead of R2?
So is it not true you can do exactly the same example in any dimension if you replace your K4 with a KD plus 2? So
yeah.
If I take K5 in R3 and I delete one edge, then I'll be able to move it up to R4. But again, I'm not sure if I understand the question.
Yeah, I'm just like you have 3 points. Sorry, where did I read? So I have now I have 3 points in R2, right? And then this is then I add the new vertices, like so. This is a coning operation with 3 edges, and suppose these edges are in this this particular length, so they are fixed. So you're stuck in R2, right? In this example.
Okay.
So now imagine I have a D plus 1 vertices in RD,
Mm-hmm.
and then I add new vertices. I connect to every point in every D plus 1 points. And suppose I choose this length carefully, then I can stuck in RD, right? So if the edge length I choose for some particular way, this is stuck in RD, like this example, this triangle example, right? It's stuck in R2 when I add a new edge with 3. When I add a new vertex with 3 edges. And now I remove one edge, like this example. I remove one edge, then I can always lift this framework to R3, right? You could rotate this blue plane.
Yes.
So I'm just saying if this is true for any dimension. I'm just asking, yeah.
So I think so, but as you say, this relied very much on the reason this was true is because you picked very special lengths for those free edges, right?
Yeah, yeah.
So I mean, it's not a kind of question I thought about before, but I guess you can make the same argument you said work in any dimension by going to sort of KD plus 2 minus an edge as the, but you have to make a nice special realization of KD plus 2, the same way your K4 was really K2 plus 2 in R2. And I guess if you do K5 and R3, etc., you'll be able to do the same. So in R3, you would start with the K4, and then you'd pick special lengths for the 4 edges, I guess.
In R3, yeah. I'm not sure. Yeah, it doesn't have to be K4. It can be anything. It doesn't have to be K4. I mean, just any D plus 1 vertex in.
Yeah, that's true. Actually, you're right, because you could do a. Sorry, I'm drawing over you now. I should move that to there. So you can do the same for a wheel. So even if you choose this vertex in the right place, it would be okay. Yeah.
I'm just saying if I have if this is not a coning option, then for any edges, I can always do this, right? I don't have to be. It doesn't have to be some particular edges. For any edges, I can always lift it to one dimension higher.
Yeah. No, I agree with you. I think you probably do need a certain number of edges on your D plus 1 vertices. Mm-hmm. You probably need some condition, but I don't know what it is. Oh, and this was D plus 2, because I was thinking about this as this graph in 2 dimensions, but yeah.
Okay, yeah, that's my question. Thank you.
Thanks, Face. Sorry, I don't think I understood it for too long, but hopefully it was useful discussion. Okay, so I've gone quite significantly over time now, so I should stop. And on Monday, I will continue with the proof of this theorem. And next week, I believe we have guest lectures by Bob Connolly. So let me just advertise that now briefly. So that's on the 17th and 19th.